It's not on.
Okay.
I can do this.
No worries, there's people are joining online, but we'll just make a start actually.
Yeah, Northland's supposed to be really nice.
All right, guys, thanks everybody for coming to today's ERI seminar. Yeah, I'm glad you can join us, and welcome to people online. It's fantastic to see quite a diversity of people in the audience today. And for those who don't know me, I'm Dennis Esconducture. I'm a freshwater scientist here at the university in the School of Science. And we're really pleased to have Kevin with us for a sabbatical. And so just a short introduction to Kevin. Kevin is an associate professor at the Rensselaer Polytech Institute in New York, USA, where he leads an interdisciplinary research team spanning ecology, biogeochemistry, development of advanced environmental sensors, and computational modeling, with a focus on understanding broad-scale patterns and processes at the ecosystem and microsystem scale. So Kevin holds the Frederick R. Colleague 52 Career Development Chair in Freshwater Ecology. He's the acting director of the Darren Freshwater Institute and the director of the Jefferson Project. Kevin's research findings have been published in high-impact journals, including Science and Nature, and featured in media outlets such as the National Public Radio, Washington Post, Fox News, and Popular Science magazine. So very privileged to have Kevin with us for the 6 months of your sabbatical, and I'm handing over to you for the seminar. Thanks.
Great. Thank you, Dennis. Thank you all for coming. Thank you for people that are online. As Dennis mentioned, my name's Kevin Rose. I've got a number of topics I'm going to cover. First, a brief introduction to who I am, sort of my study systems, where I'm from, and then talking about, the majority of this talk will be about dissolved oxygen, why it's important, what do we understand about how dissolved oxygen is changing, and then transitioning into harmful algal blooms and some research we're doing on understanding harmful algal blooms and forecasting them, understanding their dynamics. So as Dennis mentioned, I came here, is this cursor? Is that, okay, that does work. So I'm here on sabbatical. I arrived in December. So I've got my wife and kids with me. We're here at University of Waikato until July, mid-July. So I'm happy to meet with others and set up meetings after this, anytime over the next 4 months or so. I come from upstate New York, right near Albany, which is the capital of New York State, from, as Dennis mentioned, Rensselaer Polytechnic Institute. My research, as Dennis was saying, involves understanding large-scale environmental change and how it impacts lakes and freshwater ecosystems in particular. So characterizing the effects of environmental change for lakes and the organisms that inhabit them represents a major challenge in ecology. Two topics I'm going to talk about today are dissolved oxygen and eutrophication in algal blooms. Another topic that my research group focuses a lot on is acidification and recovery from acidification. That's something that's been happening in, for example, in the Northeast US where I work, but is not an issue here as far as I'm aware. So I won't be talking about that today. A lot of my study systems are in New York. So on the map on the lower left is the Northeast US, and I've highlighted the Adirondack Park in particular. That's the largest state park in the lower 48, so in the lower 48 states in the United States. And it's got about 3,000 lakes over 10 hectares or larger. If you go to smaller surface areas, it grows faster than exponentially. As Dennis mentioned, I'm also the acting director of the Darren Freshwater Institute, which is my university's field station on Lake George, which is in the Adirondack Park. It's a roughly 50-kilometer long lake, a lithotrophic lake, where a lot of our research is done. And picture on the upper right is a picture of our field station. And at this field station, we've been operating a partnership with a few other organizations, including IBM Research and Lake George Association, which is a not-for-profit focused on water quality there. With this partnership, it's called the Jefferson Project at Lake George. This is in partnership, as I mentioned, with the LGA, Lake George Association, IBM Research. We're combining a lot of cutting edge technologies. I say cutting edge, they are too often to the general public, but to this audience, they often won't be. And in fact, a lot of what we have mirrors a lot of what you have here. Vertical profilers, we have several of our own home-built vertical profilers at this point. Weather stations going up and down a lake, tributary monitoring stations on a lake, and ADCPs or acoustic Doppler current profilers that we can use to look at water mass movement, vertical, horizontal velocities, turbidity, concentration, particle movement, et cetera. We ingest all of this data plus roughly a little over at this point, 40 years of historic water quality monitoring data for visualizations. We've got something what we call a scenario engine, which is essentially long-term forecasting for different scenarios. And operationally, we have a series of different models that we use. So we run land surface and weather models down to 111 meter spatial resolution, which is incredibly fine scale. We find that actually makes our hydrodynamic modeling much more accurate, right? And the two are work hand in glove. So we use weather models and runoff models to then drive hydrodynamic models, which then we can look at runoff and pollutants like increases in salinity is something we're seeing in the Northeast US quite a bit with road salt applications. We look at circulation, water mass movement, and then the chemistry and biology, nutrient cycling, NPZ models, for example, nutrients, phytoplankton, zooplankton, et cetera, and all of these are coupled together. So that's a little bit about who I am and where I work. Now I'm going to get into, okay, show me the data, show me some patterns, show me what you've actually discovered so far. So a little bit of context for research. This is a paper by Catherine O'Reilly published in 2015, Geophysical Research Letters, using in situ data and remotely sensed data to look at summer surface water temperatures. And they showed on average a median temperature increase of about 0.34 degrees per decade. That number I'll come back to, but that's roughly what we continue to see is 0.3 to 0.4 degrees per decade. But lakes generally are warming. Some are cooling, and I could get into why in another lecture. But we know that lakes are definitely being exposed to climate change and are warming as a response. One of our first questions that we started asking in 2016 was, okay, with lakes warming, what's going to be the effect on the chemistry of these systems and biology, specifically thinking about dissolved oxygen dynamics? And what are the effects of climate change on aquatic dissolved oxygen concentrations? Why dissolved oxygen? We know that systems will undergo, if you lose oxygen, you undergo this redox ladder where you lose your aerobic metabolizers first, and then you move down with the end stage being methanogenesis. And also, not only are we going to alter the chemical reactions that occur in the water column or in the sediments, depending on the oxygen concentrations and the duration of anoxia, for example, but then aquatic organisms are very sensitive to dissolved oxygen. Some of the most sensitive species, such as certain species of trout, start to exhibit abnormal behavior starting at even 5 milligrams per liter dissolved oxygen. That's pretty high. And I used to say all complex life depends on dissolved oxygen. And that got the microbial ecologists really upset because they said, well, this is complex life too. Even just because it's single cell doesn't mean it's not complex. And I said, okay, well, then it's only multicellular life. All multicellular life depends on dissolved oxygen. Then I had a colleague come up to me from Scripps and say, that's not true either. There's some organisms in the ocean, and this paper was published in Nature a couple of years ago, that they found these metazoans, so multicellular metazoans in the ocean, surviving at basically as close we can measure it to zero, complete anoxia that they're surviving in. So I say the vast majority of life, of complex life, depends on oxygen, dissolved oxygen. So complex life in general requires oxygen. Is climate warming driving global lake oxygen loss? Is our central research question. And we started this research in 2016, as I mentioned. And then the very following year, as we're midway getting into this project, this paper came out by Schmidt-Co et al. In Nature, focused on the oceans and showing that the oxygen content in the oceans has declined about 2% since 1960. And so that's not a very large proportion, but there were a lot of areas where oxygen has historically been low. There's oxygen minimum zones, and there's coastal areas where there has been historically a lot of hypoxia. So this can push a lot of systems beyond critical thresholds in terms of biogeochemical feedbacks and survivorship of some types of organisms. But we asked, is a similar phenomena occurring in freshwaters? In some ways, we might say yes. If we look at the relationship between oxygen content and temperature, dissolved oxygen concentration goes down as temperature goes up because of the solubility of oxygen in water goes down with that. And we know it depends on the salinity of the water, and that's fairly predictable. So we asked, are lakes just small oceans? Would we expect to see similar phenomena? And we said, we would not expect the same. Why? Because the lakes are generally much more productive than the oceans. And so we have much larger gradients in productivity. And we know, for example, there's a paper from Gabriel von Droscher in 2010 showing that this is 1 over KT. So higher temperatures are actually on the left-hand side of this axis. But as temperature goes up, so moving to the left on this axis, metabolic rates also increase. So if we have a lot more productivity in our lakes than we do in the open oceans, we might expect a biological feedback that consumes more oxygen as temperature goes up. We also know we're seeing observed changes in ice cover and stratification that can regulate oxygen dynamics as well. So we asked, how are lakes responding to temperature warming? So we started this leading this project in an organization called GLEON, Global Lake Ecological Observatory Network, which is actually how I met Dennis and actually several others of you in this room. And we were able to compile a data set of about 440 lakes that had profiles of dissolved oxygen and temperature. We set a minimum of at least 15 years of data. The mean number of years of data was 24 years, totaling about 24,000 profiles each for dissolved oxygen and temperature profiles. In the center here, we show that the data spans going back to 1941. Researchers on Lake Erkin in Sweden were starting to collect data even in the middle of World War II. And that was the earliest data set we could get. The data really start to pick up around 1980, and especially 1990 onward is where we've got a lot more data, where a lot more monitoring was going on. We can see the left-hand map, the red dots indicate our study sites. We're definitely not well represented in a lot of areas of the world, right? A lot of Africa, nothing in South America had met our data requirements that we could find. But the coverage that we did have, which was primarily the US, Europe, and actually a decent amount of lakes from New Zealand, represents the distribution of where lakes are concentrated around the planet. We organized this by profiles. We separated these by surface water and deep water. So we looked at trends separately. Surface waters we defined as the top 2 meters of the water column, and deep waters in the bottom 2 meters of the water column if the lake was stratified. If it wasn't stratified, then we only looked at the top 2 meters of the water column. And we use that data set to ask, how is dissolved oxygen changing globally? Do trends vary with depth? And what explains warming-induced solubility losses? Can observed trends be explained by warming-induced solubility losses alone? So we know the systems are warming. So let's get into the data. This plot shows our surface water data, our surface water measurements. So in the right-hand side here, we can see surface water temperatures have increased and dissolved oxygen generally has decreased. Our warming rate that we observed was 0.39 degrees per decade. Recall back to what I showed for Catherine O'Reilly's paper, it was 0.34 degrees per decade. So actually relatively similar, using a lot of different lakes over a different time period. So it's good to see that consistency. The plot in the upper left shows our expected change in dissolved oxygen due to solubility changes versus our observed change in dissolved oxygen concentrations. So that means we would expect, due to solubility alone, some changes in dissolved oxygen. How much should we see versus how much should we expect to see due to solubility alone? If all of the changes were due to physics alone, just that change in solubility, all of them would lie right on that black line, that 1-to-1 line. The blue line shows the low S smoother of it, and actually that blue low S smoother actually falls very close to that 1-to-1 line overall, suggesting that our changes in surface water dissolved oxygen concentrations actually reflect our changes in solubility fairly well. There's a lot of variation across systems. A lot of that is driven by uncertainty in our trends, and a lot of those trends are fairly weak. And there are other dynamics that I can get into that explain things on a case-by-case basis. What I'm looking for here was just generally overarching patterns too. So surface waters in general, like I said, that blue low S smoother is fairly close to one line saying the population level change is well explained by changes in solubility. But that represents about a 5.5% loss since 1980. So 5.5% loss in dissolved oxygen concentrations. Meanwhile, deep water dissolved oxygen dynamics. Same plot here on the lower left, where we're looking at expected change in dissolved oxygen due to solubility changes versus the observed change in dissolved oxygen. There, there's a cluster of lakes around zero change in expected change in solubility. But on the observed change, we see a wide range of quite a large, really looks like a shotgun blast there. And in terms of temperature trends, our median trend for temperature, for deep water temperatures, was actually negative. So despite the fact that surface waters were warming decently rapidly, deep water temperatures were not warming, and dissolved oxygen concentrations were declining. And that represents close to a 20% decrease in dissolved oxygen since 1980. So I probably attribute that to the reason why this got accepted in Nature, because that's an absolutely enormous number. Part of the percentages can hide something really important, which is that the reason why it's a very large percentage, because if you look, the rate of dissolved oxygen decline is actually fairly similar to surface waters. But the percentage is a much larger percentage because hypolimnetic waters start out often at very low DO concentrations to begin with. So our median dissolved oxygen concentration at the beginning of the period was something like 3 to 4 milligrams per liter. And so when we're losing even a small amount of that, it's a relatively large percentage. So then we started to dive into, okay, what exactly is explaining these trends? Is it increases in temperature and consequent reductions in solubility? Is it changes in consumption rates? So biological feedbacks occurring. Is it earlier onset or changes in stratification that are occurring? So first, in terms of the deep water temperatures, I already gave that away, which is deep water temperatures here are not changing, right? Our trend was surface water temperatures were increasing. We saw this decadal scale pattern, which actually is driven by a lot of large lakes in Europe, mostly, that only mix every few years to the bottom. So they build up heat and then they'll mix and cool down. And so we tended to see an overarching population level trend driven by those larger lakes. But if we look at the distribution of trends and our temperature trends here, deep waters in blue are not warming. The center of that distribution is right at 0, versus the surface waters was much faster, was warming quite substantially. Another paper that came out the year before ours by Rachel Pilla et al., which actually used a lot of the same data, but not completely, there wasn't perfect overlap, showed similar trend where surface water temperatures were increasing by 0.37 degrees per decade. And they showed in their analysis, deep water trends were basically close to 0, right? They showed a very slight positive overall median trend. But our net result is that there is basically no warming across all these hundreds of lakes. And so we wouldn't expect, or solubility doesn't explain, changes in solubility do not explain our changes in dissolved oxygen losses. So with solubility ruled out, is it changes in deep water dissolved oxygen consumption rates? And so what we mean by that, if we look at dissolved oxygen concentrations on a seasonal basis, oftentimes we see something like this, where early in the season, our dissolved oxygen concentration is high. And this is north hemisphere centric. So early in the season being April, May, and June, dissolved oxygen concentrations are high when the water column is often mixing deeply, and we're getting mixing of that atmospheric oxygen into our deep waters. When the lakes then stratify, and we're talking about monomictic or dimictic lakes often here, and that's what our analysis was focused on for deep water dynamics. We often see that dissolved oxygen concentrations decrease often remarkably linearly over the course of that stratified season until the point where they sort of reach 0 and then they'll flatline for a while. And then stratification eventually breaks down in the fall and we get renewal or mixing of atmospheric oxygen concentrations. If we see an increase in deep water dissolved oxygen consumption rates, we would see this as reflected as the red line and an increasingly steep slope over time, right? Where the oxygen is drawn down more rapidly. And this can occur, for example, if we get more inputs of labile organic matter, if temperature increases, these factors can increase microbial respiration rates. Alternatively, we can see changes in stratification phenology. So this is things like the onset or duration of stratification. So similar starting diagram, but if stratification starts occurring earlier and earlier, then we're shifting that entire line to the left on that diagram. We're not changing the slope of that line, we're just shifting it to the left. So it's in parallel. But our analysis for the Nature paper was focused on the July and August time period. And so if we're looking at July and August, even if the rate of oxygen consumption hasn't increased, but oxygen consumption starts earlier, by the time we get to that July and August timeframe, then we're going to see lower dissolved oxygen concentrations. So we ask, okay, what is it? Is it both perhaps? But do we see changes in our consumption rates, or do we see changes in our stratification phenology? The other thing too, that our study actually doesn't even address at all, is that stratification breakdown is also shifting later in the year. So we focused on this July and August timeframe because we said, well, that's probably the timeframe when most lakes have the lowest dissolved oxygen concentrations. But if stratification is also shifting later, and it is, that time frame of the most severe oxygen depletion is actually probably also shifting later. And so our study period might not even represent the most critical time period for lakes in the future. So jumping into some results. This is a distribution of trends in our deep water consumption rates, right? So if our lines are getting steeper here, meaning consumption rates are increasing, we would see these consumption rates start to increase, right? And the distribution of trends would be shifted to the right here, meaning that our consumption rates are increasing over time. They were centered right at zero. The median dissolved oxygen consumption rate was centered right at zero. And at least for this was, for the lakes that we had data for. So this is a subset of the 440 lakes. This was about 150, 175 lakes for which we had these data for. And what we think is happening is we see a wide range of patterns across lakes, is that some lakes are increasing in that dissolved oxygen consumption rate. And in those lakes, it's factors like eutrophication, browning, more sources of labile organic matter. But then we also see the opposite trends, where some are actually slowing down. So that rate of deep water dissolved oxygen consumption is being mediated over time by things like pollution controls, right? Reductions in phosphorus inputs, nitrogen inputs, or some types of invasive species. For example, invasive quagga mussels and zebra mussels filter out a lot of that organic matter and improve water clarity, reduce productivity. And we've seen really clear evidence in some of our lakes where when those invasive species and invasive filter feeders come in, that we see improved dissolved oxygen concentrations as a result. That's not true, obviously, for all invasive species. So we really there ruled out deep water dissolved oxygen consumption rates do not explain overall the trend toward deoxygenation that we're seeing. What does explain it though really well? If we look at the onset of stratification, the breakdown of stratification, and the overall duration of stratification, we see pretty consistent patterns toward earlier onset of stratification by 1.4 days per decade, and then later breakdown of stratification by 2.5 days per decade, and an overall increase in the duration of stratification by 3.8 days per decade. So overall stratification, earlier onset of stratification, we believe provides more time for dissolved oxygen drawdown in deep waters, hence explaining why we're seeing much faster rates of dissolved oxygen losses and trends toward deoxygenation than would be predicted based on solubility alone, for example. Now, the concern really gets into the future here because we know that stratification is changing, and that is consistent with Now we see our surface water temperatures increasing, but our deep water temperatures are not increasing. So the temperature difference between our surface waters and deep waters is increasing. That acts as a greater barrier to mixing and a greater barrier to atmospheric renewal of oxygen into our deep waters. Projections by Yes and Woolway, published in Nature Communications in 2020, show that exactly what we've found is what we expect to see over the coming decades. So we showed that we're looking at, as a trend, 3.8 days per decade overall increase in the duration of stratification. And they showed that over the next 80 years or so, under the fastest warming scenario, the red line, for example, we're expecting to see another up to a month or more increase in the duration of stratification. So it's likely our data indicate that we see widespread deoxygenation occurring, driven largely in deep waters by earlier onset of stratification, and this is likely to continue into the future. And that just summarizes, so warmer temperatures, so to summarize the dissolved oxygen section here, dissolved oxygen, the warmer temperatures is causing reduced DO solubility in our surface waters. Consistent with ice loss, warming temperatures, climate change is shifting the onset of stratification earlier, resulting in more time for deep water deoxygenation. The breakdown of stratification is also shifting later, so the severity of DO losses is perhaps greater than our analyses indicate. And that time period is probably shifting to the early to late fall when ecosystems, when deep water habitats are becoming the most stressed. And deoxygenation is projected to continue or perhaps amplify in coming decades. From a management perspective, dissolved oxygen is critically important for nutrient cycling, for aquatic habitat, for organisms, et cetera. And the question becomes, how do we locally manage DO concentrations when the dominant driver of deoxygenation is a global process, right? Remember I said it's not due to changes on the net of changes in productivity, for example. Now it will be, and when we see, for example, increases in productivity in places, that'll amplify these problems. But this becomes a challenge for water resource managers. And I think the answer is that this puts even more emphasis on the need for proactive management to reduce nutrient inputs, to reduce organic matter loading, et cetera. Okay, stepping bigger picture for a minute, I showed the paper from Schmidt-Co et al. 2017 that showed global oxygen losses in the oceans. Denise Breitberg also has a paper on showing hypoxic areas in coastal zones all around the world, published a review paper in 2018 in Science. And deoxygenation is really a global phenomena, and now it's been consistently shown across from the open oceans to the coastal zones to inland waters. Then there's even been some recent papers that are showing that this is increasingly a problem in river systems as well. And so working with Denise Breitberg, her group, and some other oceanographers, we just had a paper accepted in Nature, Ecology, and Evolution proposing deoxygenation as, I'll get into this more in a minute, a new planetary boundary. And take home here is that if we look across marine systems to coastal zones to inland waters to including lakes, reservoirs, and rivers and streams, deoxygenation is caused by a small number across all those different types of ecosystems. In A, reduced solubility under warming. B, increases in stratification, strength, duration, et cetera. And C, increases in organic matter loading or nutrients, phosphorus, and nitrogen. All three of those things, the relative importance of those varies based on our ecosystem type and where we're located, but those are the common drivers across it. Why does this really matter? Well, Rockstrom et al. In a paper published in Nature in 2009 and then followed up by a review by Stefan et al. 2015 in Science proposed what they called planetary boundaries. And this is a series of 9 interacting Earth system processes that regulate the stability and habitability of the planet. And they talk about things like freshwater use, land system change, land use, land cover change, novel entities being things like microplastics or PCBs or other things, climate change, biosphere integrity, meaning extinctions per 1 million species years, stratospheric ozone depletion, atmospheric aerosol loading, et cetera, et cetera. And when we look at aquatic dissolved oxygen, not only looking at freshwaters now, but looking at marine ecosystems and coastal ecosystems, aquatic dissolved oxygen and the trend toward deoxygenation regulates a lot of these other planetary boundaries and sometimes in complex ways, right? Aquatic dissolved oxygen, by altering whether the dominant form of metabolism can be anaerobic or aerobic, alters the whether or not we end up resulting in CO2 production or methane production, and hence feedbacks to climate change, and regulates the rate of organic carbon burial or nitrous oxide production, et cetera. And so we're proposing that aquatic dissolved oxygen represents a planetary boundary because it's both impacted by these other changes, like I just talked about climate change and stratification, but then it also has these really important feedbacks to these other planetary boundaries when aggregated at a global scale. Okay, so that summarizes what I want to talk about with dissolved oxygen, trends and patterns in lake dissolved oxygen, drivers of lake deoxygenation, and proposing deoxygenation as a 10th planetary boundary. Now I'm going to get into harmful algal blooms and relating that to dissolved oxygen dynamics, but then moving a little bit into a new space that my group has been working on and trying to forecast changes in productivity and harmful algal blooms. So another central question we've been working with is how will lake productivity respond to climate warming? First, productivity and dissolved oxygen are coupled, right? Higher productivity, we often see higher concentrations of dissolved oxygen in surface waters, for example. Productivity controls carbon cycling, fisheries, water quality evaluations, et cetera. We know harmful algal blooms are a manifestation that occurs when we often get high productivity, but not necessarily. And harmful algal blooms pose substantial economic and ecological threats. There's lots of reviews on this we can get into. People are interested in. There's multiple ways we can, let me step back for a sec. Multiple ways or pathways by which people have proposed that climate change will influence productivity or lake productivity. The first hypothesis is climate warming will increase lake productivity. The temperature, just due to the temperature dependence of primary production, for example, that we would expect to see an increase in productivity as temperature goes up. And we would even more specifically expect to see more cyanobacterial blooms or harmful algal blooms. Paper by Pearl and Weissman et al., Pearl and Weissman 2009, should look at the thermal performance curves of different types of phytoplankton. And the two thermal performance curves that top out here at over 20 to 25 degrees C, these are both cyanobacteria. So we know that cyanobacteria tend to do better under warm conditions. And so one hypothesis might be as temperatures increase, we would expect to see higher productivity because of that or as a result. However, a contrary hypothesis might be, well, it's not just temperature that regulates productivity in harmful algal blooms, for example. There's things like nutrients matter, right? And as we increase our temperature, first, if we look at a curve here, the blue line might be historic temperature and a historic nutrient concentration gradient through the water column. We know that deep waters, when a water column is stratified, deep waters tend to have higher nutrient concentrations. And if we're extending and strengthening our duration of stratification, we would expect to see more depletion in our surface waters of nutrients and higher concentrations in our deep waters. And so perhaps then it's not driven by temperature at all. Perhaps what we would expect to see in future conditions under warming is more nutrient limitation of cyanobacteria in our surface waters. So what is it? Should we see increases in harmful algal blooms and cyanobacteria, or should we see decreases? The literature on this is really mixed. Ho et al. Published a paper in 2019 in Nature using remote sensing to look at bloom intensity in about 75 lakes around the world. Let's see if we can get that to disappear.
You can click more and then hide the video.
Floating media.
Floating.
Yeah, thanks. Okay. They showed in this paper that peak summertime bloom intensity had increased in about 2/3 of lakes, showing that there's evidence of widespread increases in at least surface blooms, potentially cyanobacterial blooms, in lakes around the world. And then another paper by Grace Wilkinson published in 2020 showed that if we look at distributions of the magnitude, severity, and duration of cyanobacterial blooms from about 300 lakes across the United States, that overall, if you look at those distributions, they're really balanced. And overall, the magnitude, severity, and duration, the percentages are on the negative side, meaning that overall the magnitude, severity, and duration of blooms has decreased over time, not increased. So now we've got two conflicting studies using very different methods and different systems. So it's not necessarily a surprise that they're going to conflict with one another, but there's not a consistent story here. There's not a consistent message of saying, warming, or we're seeing a trend toward increases in productivity, increases in algal blooms, or the opposite. So we went back to our dissolved oxygen data set and said, do we have anything to say about this? And that sounds like the way I said it is not actually how it occurred. The reality is we found this really cool phenomena where if we look at the number of lakes where we have increasing versus decreasing surface water temperature trends, and then we looked at DO trends, right? Recall that we should expect to see under solubility in our surface waters, right? As surface waters are warming, we should see decreasing dissolved oxygen solubility. And we see that in 224 lakes out of whatever 224 is plus 87. We see the vast majority of them are decreasing in surface water dissolved oxygen as conditions are warming. But there's 87 lakes that are increasing in surface water temperature and increasing in dissolved oxygen solubility. Well, that doesn't make sense. Physics would say that shouldn't be happening, right? So that's where we looked at that and said, what else is going on there? And so then we extracted those lakes from our overall population and looked at how they're responding differently. And those are the trends. The red lines are the ones that had this increasing in surface water temperature trend and increases in surface water dissolved oxygen concentrations. So if we look, and the blue ones are minus those, right? All of the 224 other ones. Obviously, the black line was all of them together. So we can see they're not really different in terms of warming rates, right? Nothing considerably different is occurring there. But then obviously the dissolved oxygen curve is very different there. We can't do the same for deep water dissolved oxygen concentrations because interestingly enough, most of those lakes that had that red curve there had no trend in deep water dissolved oxygen concentration because they were consistently anoxic for the entire time period, which should tell you something about what's driving it. So unpacking this a little bit, we put together this three-dimensional relationship between dissolved oxygen, water clarity, and temperature. Recall, we were pulling 400 lakes from around the world and pulling as many data sets as we could. We didn't have a lot of other data to support this, but water clarity is one of those things that we can remotely sense on every lake. And what we find here in general, let me do this with the cursor here, as temperature increases, dissolved oxygen decreases, right? We see this general curve of downward as temperature increases down this axis. Right, dissolved oxygen concentration tends to go downward until you get to really low water clarity. It's up here, right? At that point, then, at the top of that graph, as temperature starts to increase, DO decreases until you get to a threshold of about 24 degrees C. And above that threshold of 24 degrees C, we start to see that positive feedback, but only when water clarity is low. Similarly, if we take a plot and look at for the lakes that we had data on, which is I think 77 lakes or so, mean chlorophyll concentration, and then our dissolved oxygen trend, when the temperature is cold, so 21 degrees C, the blue line, regardless of summer productivity, our DO trend was negative. When temperatures were moderate, 25 degrees C, there was no trend in dissolved oxygen. And when surface temperatures are warm, we see DO trends increasing over time, showing this interplay between what looks like measurements or indirect proxies of productivity and its effect on dissolved oxygen. And here's indirect evidence of what we think is happening is that as temperature is warming, we're potentially seeing favoring cyanobacteria dominance of these systems, especially in more productive environments where water clarity is very low, summer chlorophyll concentrations are high. And we especially see this at a threshold of about 24 degrees C and above, is where we're starting to see evidence in the dissolved oxygen data of increases in productivity over time. Now, this is, in a lot of ways, it's very circumstantial and very speculative, so we don't talk about it much in the paper because we don't have any phytoplankton data to talk about what's actually changing here. But this is consistent with what we'd expect to see if we, with increases in cyanobacterial blooms. Okay, so the dissolved oxygen data set gave us an in to try to start to understand more about cyanobacterial blooms. More generally, one of our research goals is to forecast future changes in harmful algal blooms. But to do that, first, we really got to understand their causes. And so we've been examining for the past couple of years, what are the right conditions for harmful algal blooms? This is a picture of beautiful Lake Erie. That's the water supply to the city of Toledo, Ohio, for example. The drinking water intake was shut down to 400,000 people in 2013, 2014 because of very high microcystin concentrations in the water supply. So we don't do work in Lake Erie. I just think that picture is really impressive. So what are the right conditions for harmful algal blooms? We tend to think of them as manifestations that occur when we have high nutrient concentrations, we get warm temperatures, calm conditions. That's when you get a cyanobacterial bloom. But we know it's a lot more complicated than that. And so in high productivity systems, yeah, that might be accurate. But we've also started to see harmful algal blooms occurring in systems that are more oligotrophic in nature. We're doing research on Skinny Atlas Lake, and this is one of the Finger Lakes in Western New York. It's also a drinking water supply to the city of Syracuse, so it's about 200,000 people depend on the drinking water that comes directly from this lake. In 2018, so the lake had its first ever recorded toxic cyanobacterial blooms in 2017. And so we deployed sensors in 2018 to try to understand what was driving these harmful algal blooms here. We deployed a vertical profiler with ADCPs, our acoustic Doppler current profilers, top and bottom. The water column collected weather, water quality data, acoustic, that's the ADCP data. And then we calibrated a three-dimensional hydrodynamic model to try to understand mixing dynamics. When we had our sensors out, there was 8 confirmed toxic cyanobacterial blooms in the lake. Where I'm going to show you, we didn't deploy over the deep hole in the lake, the deepest spot. We deployed right in this basin and north end of the lake. And you can see here where it's a lot deeper further down. It's something like 210 meters deep overall. You can see as you move up north of the lake, quickly, there's a shelf here. And we're just shallower than a shelf at about 20 meters deep. So first, if you're not familiar with an internal seiche is where we get, the surface waters might be perfectly calm at the surface, but you get distinct layers in the water column, epilimnion and hypolimnion separated by that thermocline. And if you get strong, persistent winds in one direction, you can have a buildup of epilimnetic waters on one end of the lake, which forces the hypolimnetic waters to shift to the other lake. And then when that relaxes, when that wind lets up, you can get waves across that thermocline that transit down the length of the lake. You can predict what the theoretical length, the period of these waves should be based on the attributes like the bathymetry and length of the lake. Anyway, that's just an internal seiche, or a description of what it is. But I want you to know too, you might not see any evidence at the surface. So your epilimnetic, like if you're measuring sensors only at 1 meter deep, if you've got a buoy there, you might never see any evidence of an internal seiche. But fortunately, we had our vertical profiler there with our ADCP data. And we see this repeating early on in our deployment period. We see high wind speeds. And typically for this lake, we saw internal seiches when we got above 5 meters per second down the length of the lake. And that set up this internal seiche, and we can see this evidence of it, of this very periodicity, this increase in cold waters, right? Because we were sitting at 20 meters deep. The thermocline depth was about 16 or anywhere from 12 to 18 meters, sitting at about 16 meters on average. And you can see that here, this transition between our warm surface waters and our hypolimnetic waters, this seesaw pattern, right at our theoretical period of just under 24 hours. that SACE is moving backward and forward. If we look also in our ADCP data, we can calculate our velocities northward and southward in the lake and in the vertical velocities as well. And we can see right at about a 24-hour period, just under a 24-hour period, the system transitioned from a southward velocity to a net southward velocity to a net northward velocity right at the lake bottom, which shows that that wave is coming up and then coming back, rocking back and forth right around where the buoy is located. And we saw that consistently many days throughout the summer. Our calibrated hydrodynamic model also shows this, right? So we can see those waves transition down. And so you can see it right here where it'll hit. This will repeat in a second. And you can see the wave transit down the across the thermocline of the lake. And when our buoy was located right about there, and so when that comes down the length of the lake, the change in color tells you the speed of the velocity of the internal wave. We can see it crash into the sediments right there, right? And so we saw that, and it was followed really quickly by, again, the top is our velocity southward to northward, and we can see that transition. But immediately after it transits across there, we see this plume of turbidity increase. We see it in our turbidity data at the lake bottom. We also see it in our backscatter data in the ADCPs, indicating particulates coming out of the sediments. And essentially what we see happening is that wave, go back to the animation here, when that wave transits down, it crashes, just like a wave on the beach, it crashes into the sediments. You don't see any evidence of it at the surface whatsoever, but it's crashing into the sediments right there in that 12 to 16 meter layer around the lake, and it's stirring up the sediments, and there's very loose flocculent sediments there. What's there? I'll talk about that more in a minute. Anyway, we see that each time that internal wave transits through the lake. Now, we can model tracer diffusivity, and we see the amount of energy imparted into the sediments is actually greatest right around. We happen to get very lucky where we put our vertical profiler to see that on that north end of the lake where that wave comes in and crashes into the sediments. Again, that's where our vertical profiler was located. And if we look at phosphorus concentrations in our sediments, they're pretty substantial, especially as we decrease in depth. And that blue band from about 12 or 10 to 20 meters is the maximum band at which we saw this phenomena occurring in a sediment. So we know that now that internal SACE rakes the sediments and mobilizes phosphorus-rich sediments into the hypolymnia. It's probably also mobilizing lots of other things in the sediments too, like inactive cyanobacteria cells. So that's the first sequence. That's the first event that we saw. The next event that we saw was, okay, well, we've got sediments that are released into the upper water column by this internal wave crashing into the sediments. How does that released sediment actually get into our surface waters, though? How do we mobilize that through the thermocline, for example? And there, in our ADCP data, we see Langmuir circulation. We see something specifically called Langmuir supercells, which is Langmuir circulation occurs when you've got strong persistent winds down the length of the lake. You can get these helical coils develop, right? That you can get convergence zones that form windrows on lakes, and you'll see them on a windy day in a lot of large lakes. Where you get a lot of surface concentration, a lot of surface aggregation. And when these operate, when you get Langmuir circulation at the same time as you're getting an internal wave, as that internal wave passes by and that thermocline dips down deep, at the same time that you've got Langmuir circulation, those Langmuir cells can reach all the way down to the bottom of the lake, meaning to where the internal SACE depresses the depth or decreases the depth of the thermocline. So we can see Langmuir circulation pushing and pulling water up from 16, 18 meters deep. So that internal SACE mobilized sediments into the hypolymnion, and then we saw Langmuir circulation pulling those sediments up to the surface of the water. And we can see this, for example, in our vertical velocities from our ADCP data. we can look at a lot of the striping, for example. And we can see the striping in our vertical velocities oftentimes alternate at very high frequency between upward and downward velocities. What we know now was occurring was that those Langmuir cells were transiting past our ADCP, and we're seeing the combination, the upward and downward velocity of those Langmuir cells pretty close to one another. And if we look at our backscatter concentrations, for example, we can see it pulling material from the surface of the water down deep. And I mean, we also see some other interesting things in pulling it up. This vertical line here is just our ADCB capturing our vertical profile, lowering the saw through the water column there. Okay, and there's, pulling the material off of the surface, and we can see the vertical velocity here is consistent from 12 to 18 meters deep, meaning the entire water column there is circulating, moving all upward or all downward at the same time in consistent fashion. So putting these components together, what we saw in 2018 was that we had three sequence of events. First, we had an internal wave disturb the lake sediments and upwelled sediment constituents. As I said, definitely phosphorus in the sediments and probably a lot of inactive cyanobacterial cells. That was followed by strong persistent winds that resulted in Langmuir circulation that circulated that material up to the upper part of the water column. And if that was followed by what we classically associate with cyanobacterial bloom conditions, calm, warm days, that's when we had cyanobacterial blooms. That sequence of events happened 8 times in 2018, and every single time it was associated with algal bloom. There was a lot of days when it was nice and warm and calm, but it wasn't preceded by those events beforehand. And so we didn't get cyanobacterial blooms. Or we started to get, we started to get seiches, and we had seiches, and then we had Langmuir cells, but then that wasn't followed by calm days, and vice versa, right? We had lots of combinations of 1 or 2 of this sequence, but we required, if that sequence of all 3 events only happened 8 times, it resulted in 8 blooms. So it is, again, it's circumstantial evidence, but we think it's fairly strong. And we think it now means we've begun developing forecasts to predict cyanobacterial blooms based on this sequence. And we started this all out with ADCP data, these are expensive instruments, they generate a lot of data, and it can be difficult to handle. But now that we've developed this relationship between wind speed and internal seiches, and wind speed and Langmuir circulation, for example, now we can develop much more parsimonious models based on just wind speed and direction, and to assess when these different hydrologic conditions, these hydrological phenomena are occurring to better predict cyanobacterial blooms. Anyway, I don't know why that's out of order. To summarize the section on harmful algal blooms, dissolved oxygen data provide indirect evidence that algal blooms are increasing in lakes around the world, evidenced by increasing DO concentrations in surface waters despite reductions in solubility. Harmful algal blooms in our lakes, at least in an oligotrophic lake, are preceded by a defined sequence of hydrodynamic events that we think facilitate bloom formation. Characterizing these processes in real time is now enabling us to better forecast blooms, and with the right sensor network and modeling in place, we can predict blooms up to days, perhaps weeks in advance. It depends on the sequence of events, right? And so how well can you predict a warm, calm day? We're limited by our weather forecasts, but we're developing now harmful algal bloom forecasts. Anyway, that's it. I want to thank everybody, and I want to thank the team behind this. There's a lot of people that have contributed to the research. I've talked for an hour. I've actually done very little of this research. It's all been my team. And so I want to thank all of them and all of you for paying attention. Thank you.
Thank you very much, Kevin. I think we have maybe a few minutes for questions. Julia, fire away.
Thank you. I was going to say, have you seen the paper? It might be really useful for this later stuff. There's one by Nielsen and Henderson and LNO where they look at an internal seiche on a sloping lake bed in the lateral, basically the lateral protrusion of sediment. So that check it out. That might be useful.
I'll have to look it up. I'm not sure. Yeah. Where there's another paper, Kasu and Wells, 2003, that we've used for a lot of this. I'm not familiar with the one you've mentioned.
Yeah, so that's, might be useful. So I have a couple of questions. My first question is, have you looked at the periodicity of it? So you said that surface, when you've got the Langmuir circulation, you've got the up and down velocities. Have you done some time series analysis of that to look at the periodicity, and does it match what you would expect from the Langmuir cells?
Yeah, good question. I don't think we have. Good suggestion, though. Thank you. Yeah. Some of it, the challenge is the upward and downward depends on where we are relative, because those cells are moving across the lake at the same time, passively. Because there were times when we saw what looked like complete upward, and then immediately following it, seconds later, by complete downward. We're like, how is that possible? The entire lake is moving upward and downward. And we're like, oh, we think we're transiting. Those cells are moving past the ADCP, cone. And so we're seeing, the upward side of that cell, and then the next cell over, the downward side of it. So it's difficult, like that time varies quite a bit, I think, based on the speed and how wide those cells are, and then where in the cell we're looking exactly relative to where our sensor is located.
Sorry, I have two questions. The first question is more technical. When you say use sensors, with the right sensors, you can predict unfallable bloom. Are you talking about sensors only at the surface, or are you talking about sensors throughout the water column?
Yeah, these were vertical profilers, so these were through the water column, and so it's on a winch and it's raising and lowering that. So the ADCPs are inherently, they're measuring through the entire water column, minus the bottom meter and top meter, just due to interferences with the surface and whatnot. But it's mostly through the entire water column is what we've seen. Could you do it with less? You might. I don't think, I'd have a tough time getting to the mechanism, explaining why blooms are, but once you've gotten to a mechanism, then you might be able to develop a more parsimonious model based on things like a temperature string and wind speed data.
And vertical shift as well, right? So because I asked that question because, of course, it's a lot easier to put sensors on the surface than it is on ADCP on the bottom, right?
Yeah.
So, okay, my next question. Have you heard of free living anaerobic ciliates?
No. Okay.
So you have to add one more statement to your.
One more qualifier.
So look up Lake Zug, Z-U-G.
Okay.
In Switzerland. So that's where a lot of this work has been done on free living aquatic anaerobic ciliates.
Okay.
So that actually has implication, not more than just compromising your statement. I think that actually has that has relevance for how increased duration and perhaps depth of anoxia can shift the ecosystem functionality of the lake system, because Lake Zug is permanently stratified.
Okay.
Right, and that's what allows these anaerobic ciliates to persist. But of course, if the trajectory continues, many lakes will become permanently stratified.
Yeah. Okay, thank you. I'll check that out.
Awesome. Julie, I'm just checking online if we have maybe questions from the online audience. Please feel free to use your microphone or the chat function. Maybe one more question from you, Julian, and we'll see.
Yeah, there's anyone online or not. So I was just looking at your first section. Have you looked at any of is it possible to tease out any of the other physical drivers? Changes in wind speed, changes in wind direction and precipitation? Because that might influence presumably what's going on in the Apollinean.
Yeah, we tried to do that. We tried to look at, and then over different antecedent time periods as well. We looked at temperature and precip, and like I said, precip aggregate over different time periods. There, the precip didn't come up with anything that looked explanatory. Wind speed, so we're using gridded
direction might play a role, presumably.
Yeah, very well. Yeah. The wind speed we used ERA 5 gridded climate data and then interpolated to for the lakes. I don't trust wind speed to be that accurate for the lakes. So that precip maybe especially historic. I do think precip is important, and it can be really important. It's driving a lot of these changes in a lot of lakes. Wind speed probably is. I'm skeptical that wind speed can be important, but there's been a paper, there was like global stilling paper in 2009 or something like this that showed that wind speeds over the terrestrial landscape have slowed for several decades. Then there's a paper that came out in 2019 that showed, oh no, now they're recovering. And so it's like, okay, are they increasing? I don't think there's a consistent pattern of wind speeds that would drive the consistent pattern in oxygen that we would see. But precip, absolutely. But I think it's far more variable based on the region and what you'd expect to see. And then it can alter the temperature, it can alter the mixing, it can deliver a lot of nutrients, organic matter to it. So it can do it based on a lot of different ways. And it probably is this interplay between how much precip at what time of year and what's the residence time of the system and what's in the watershed. So it's like it gets really complicated really quickly. So it was difficult to untangle that. But it probably does explain a lot of the residuals that we see in the trends.
So you need to find a couple of like model systems and instrument the crap out of them.
Yeah. And they probably are. Even the systems here is probably like, you could probably disentangle that in a subset of systems. Yeah.
Awesome. Well, thanks for the questions. I think we might call it close, because I think people have to go to other places as well. So thank you very much, and please join me. Thank you, Kevin, again for the seminar. So on behalf of the Environmental Research Institute, we'd like to give you a little present, Kevin. Thank you very much.
Thank you.
Cheers.